Hello, it's Keith here, and this is the first of the so-called ChibiFighter tutorials. These are based on a little mini demo game that I've made, which is called ChibiFighter, unsurprisingly. Now, this is sort of a parody tribute of Street Fighter, obviously, as you can see here. Now, basically, it's not really a full game. It's not really been tested enough, but it's intended as a demo for a variety of other sort of programs I've been working on. One is the Chibi Tracks music software, which is handling the sound effects and the music here, and the other is the so-called Mintile graphics, which is what is doing all of the graphics, the tile map and the sprites. And these are both multi-platform solutions that exist on all of the systems within my tutorials, give or take. So this game was really just designed as a demo for that, and what we're going to do is we're going to be looking over some of the code and seeing how it works, because I think maybe some of it might be interesting to you. Now, what we're going to be discussing today is patterns and super tiles. Now, what are these? Well, patterns are the tile graphics, the bitmaps that we're using for the 8x8 tiles. Now, when we've got graphics in our game, this game in particular has various backgrounds for the different levels, and these will get quite big because the screen is 32 by 20 if you ignore the top strip. So each of these tile maps is that size, and this becomes quite big when we are in a single load, because there's not multi-loading, and when we've got multiple levels. So what can we do to make these smaller? Well, one common solution is, instead of storing the individual tiles, we combine those tiles into grids, in the case of this 4x4 grids, and these are known as super tiles, and then we use combinations of those super tiles to make things smaller. Now, this example has actually gone even further, and we've used some simple compression to allow these super tiles to be even smaller than that. So let's go and let's take a look at what we've done with these super tiles. Now, all of this was done in Sprite Editor, which has been upgraded and modified to support tile maps and super tiles. So basically, if we look at Sprite Editor here, we've got this new tile map functionality, and we've enabled the super tile option here. And you can see this first sprite here is the bitmap patterns of the basic tiles themselves here. Now, tile 0 is transparent within the Mintile graphics routine that I'm using, so that's unused, and then the rest are functional graphics bitmaps that we may choose to use. So these are the pixel maps that are available to us, and then what we've done with the next sprite is we've built these into 4x4 tiles. So you can see that the checkerboard pattern here is representing the 8x8 pixel tiles, and we've combined a 4x4 grid of 16 of these into a super tile. So this first super tile here is completely blank. This one is a sort of a dark wall pattern. This is a filled wall pattern. This is part of the floor, and we've got some various other effects here we may wish to use. What we then do is we then use these super tiles, which you can see in the bottom of the screen here as a palette of super tiles here. And we can then use these for this area. For example, we want to change part of this. We can select one of our super tiles by clicking down here, and then we can click in this area here, and we can fill these super tiles into this tile map here. But then when we want to export, well, we're actually only exporting the data that selects those particular super tiles. So we've got a very, very small amount of data indeed that we need to represent this large 32 by 24 area. So that is the concept of the super tiles that we're using for today's example. Okay, so how do we actually store the super tiles? Well, as I say, I've actually sort of reduced them even further than the basic concept may suggest. What we've done is each of these levels has a different super tile, and these are the super tile data. So this is the super tile map. Now, the first byte is the number of super tile lines, so 5 times 4, because there's 4 lines per super tile, so that would be 20 lines of tiles in total. The screen is 24 tall, and the top 4 tiles are the enemy, the scores and the life and things like that. So that's why our game area, this sort of green area here, is 32 times 20, and as I say, each of the super tiles is 4 tiles tall, so 5 super tiles times 4 is 20 tiles in total. Now, each of these lines is going to be 8 super tiles wide, because each super tile is 4 tiles wide, and 8 times 4 is 32. And so what I've done is basically I've stored one super tile number in each nibble of these bytes. So 4 bytes represents 8 super tiles, which represent 32 tiles total. So 5, 7 here in that first hexadecimal byte is super tile 5 and super tile 7. And the word here, supertile 4-byte LUT, this is the definitions of each of these possible supertiles. So supertile 20 there, you can see that is supertile 2 followed by supertile 0. And if we have a look at these LUTs, these represent the possible supertile definitions, and all of these were exported with the AccuraSprite editor. So each supertile definition is a total of 8 bytes. Now there are 16 tiles in each supertile, and so how am I compressing 16 tiles into 8 bytes? Well, there would be multiple options. One would be I could use nibbles again, and that would allow me to do that, but that would limit me to a total of 16 possible tiles, and that wasn't going to be really very satisfactory. So what I've done instead is I've used the first 4 bytes as a lookup table, as an index if you will, of the possible pattern numbers that I'm going to use. You can see we've got a wide variety here, and so this is the patterns that we're going to use, and then the second 4 bytes are a 2-bit per tile selection of those patterns. And so if we look at this supertile definition here, this is one set of 4x4 tiles within the final tile map. The first line here is defining that the bit combination 00 is pattern number 4, 01 is pattern number 10 in hexadecimal, pattern 16, 10 is pattern 14 in hexadecimal, and 11 is pattern 0. So those are the 4 possible patterns that are being used within this tile. And then you can see here that this byte here is actually one entire horizontal line of the supertile, and so the 4 bytes are the 4 lines of the supertile. And so you can see here that the first 2 bits there are 0, so that's pattern 0 in the lookup, which is pattern number 4. The second 2 bits are also pattern 0, which is pattern number 4. The next 2 bits, the 3 there, that is 01, so that will be using the entry 10 there, that's pattern 16, and then the fourth tile along in this super tile is 00, so that again is pattern number 4. Now this of course effectively means that our graphics can only use 4 possible different tiles within the super tile, or it will not be able to be exported in this format. And you will notice here, if you look at these super tiles, you will never see more than 4 tiles in total, 4 different tiles in total within each of these patterns. I've been restricted here, so you can see here this one I think is using all 4, but one like this is just using 1 pattern. It varies, but as I say, it is a technical limitation of this compression technique that I can only use a total of 4 different patterns within the super tile, and I can only use a total of 16 super tiles within the super tile map. Now I've got around this by some of the later levels using a different lookup table, because I did need more than 16 possible super tiles there, but that's a workaround there. So that's the super tile theory, and that's the data that's being used to generate the backgrounds, these green levels that you can see here. So let's take a look at the code that's actually doing the loading of the super tiles. Now this function load supertile map nibble will actually load in the supertile data from the compressed array that you can see there, and it will decompress it into the memory, and then the tile map routines will draw from that memory, and that memory is 1 byte per pattern for a maximum of 256, so it's basically completely uncompressed. Now you can see we're using this load supertile map nibble here, and what we're basically doing here is we are loading in the top strip, which is just a single super tile tall, 4 tiles tall, and it's this data here. Now the text, the numbers and the life bars are actually drawn in later, because it wouldn't be possible within the super tile definition of 4 maximum patterns per 4x4 grid. It's just the borders of the life bars basically, and the black area behind them. So this is how we're executing it, and what we need to do basically is load IXL with the offset of the pattern numbers. So this will depend on where in our pattern definitions, our 256 defined patterns of the possible graphics that can be shown, that we want to start from. Now in the case of the background, we're actually starting from tile number 0, but in the case of the level backgrounds, the green areas, we will want to start from a much later number, and we will need to skip things like the font to do that. But in this case we're loading from 0. Now we're loading our destination tile map into the shadow register HL here, because we're flipping with EXX there. So that is the uncompressed tile map in memory that we actually want to show to the screen later, and we're then loading the source super tile map into HL here, and we're calling load super tile map nibble here. And so that is the source data. Now in the case of the top strip, it's just one supertile tool, four tiles, and we've got a special supertile map here that we're using, and we can see that somewhere. Where is it? Here it is. So this is the supertiles to define the surroundings of the life bars here, and so that's what we're using to draw them. So that's what we will be using in that case. Now this supertile loading code you can see just here. And so let's go through what it's actually doing to decompress that data. Now the first thing we're doing is we're loading in C. This is the number of lines in supertiles, in four tile tall blocks that we need to load in. So that is our line count there. We're then loading in basically IY from the HL source. So this is setting IY to the address of the supertile lookup table here. So that's now in IY. We're then loading B with the number of bytes to load in from each horizontal line. Now remember, there are 8 supertiles across the line because there's 4 tiles per supertile, and there are two supertiles per byte because we're using both nibbles of our bytes in our data. Because when you see 0, 1 in this byte here, that is actually 2 supertiles. That's supertile 0 and supertile 1. That's supertile 1 and supertile 3. That's supertile 4 and supertile 1. And that's supertile 1 and supertile 2. So that's 8 supertiles in total in those 4 bytes. And so that is why we've got a byte count of 4 here, because there's 4 bytes per horizontal line, 8 supertiles. We're always doing the full width of the screen. So what we're doing here is we're loading in the accumulator from HL, and we're basically keeping only the top nibble here, and we're shifting that to the bottom, and then we're running this copy one supertile routine, which will decompress that supertile. We then need to do the second supertile within the byte, so we're taking another byte from the same HL address and moving to the next one, and this time we're keeping only the bottom nibble. So here we were processing the top nibble, and here we're processing the bottom nibble, and in both cases we run this copy one supertile 4 byte here. Now at the end of each line, what we're basically going to do is we're going to move down one supertile strip. Now we will have moved across effectively 32 bytes during the processing by copy one supertile. Another thing that's important to know is when we've decompressed into memory, our memory tile map is not 32 tiles wide. Our screen's 32 tiles wide, but so that we can scroll, we have one extra supertile that is off screen. So our tile map in memory is actually 36 tiles wide, not 32. And so we're calculating the amount we need to add to HL to move us down one full supertile strip, so that when we do the next line, we're starting directly below the first one, and that is that calculation there. We're then simply repeating until we do all of the supertiles that we loaded in from our count here. So this is just moving through the screen in basically 4x4 tile blocks, doing our supertiles, and then moving down and as required continuing until we filled our entire tile map. That's what that's doing. Now the work of decompressing the supertiles is being done by copy one supertile 4 byte LUT, lookup table LUT stands for. So this is basically decompressing this kind of data here. Now this first line here is our lookup table, or our indexes if you prefer, and our second line here is the 2-bit per tile data that we need to look up in that index, and that is what is going to happen here. So how do we do this? Well, the first thing we're doing here is we're loading DE with the address of the lookup table, and then we're transferring that into HL. So HL is now our lookup table base for the supertiles, and then what we need to do is we need to add the supertile number as an offset to that table. So what we're doing here is we're loading BC with the supertile number, and we're effectively multiplying by 8 here, because it's 8 bytes per supertile definition within that lookup table. I apologize, I know this is confusing, but when you're trying to do tile maps and things, it's going to get difficult, unfortunately. So you can see here there's 4 bytes in that first line and 4 bytes in the second line, so there's 8 bytes in total per supertile definition here. And so that's why we are multiplying by 8. And so we're adding to HL here, but then we're transferring to DE. So DE is now the 8 bytes of our supertile definition. Now what we're doing here is we're setting bit 2 of E here. We're effectively adding 4 to the DE definition here. And this is so that we're skipping the indexes and we're moving straight to the tile 2-bit definitions here. And what we're going to basically do is we're going to load in 4 lines, and we're going to load in 4 per line, and we're basically going to process each of the 2-bit pairs for the tiles within each line. And so we're loading in the byte from the definitions, which, as I say, is these bits here, and these will define, if I look at one that's a bit more varied, these will define the tile numbers that we actually want to show. So we've got 1 byte per line here, and we're loading that into C here, and then we've got 4 tiles in that are 2 bits each. Then what we're basically going to do is we're going to take our DE pair here, and we're going to basically clear the bottom 3 bits of the DE, the E part of the DE pair, and this is pointing DE to the indexes now. So these are our indexes for the tiles that we're loading in from the 2-bit pairs that are currently in the accumulator here that we moved to C. So we're going to shift 2 bits out of C into the accumulator here, and we're basically going to set those bits in E so that the DE pair now points to the matching index that is defined by those 2 bits within our lookup table, our index here of the possible tile numbers. And so if, for example, we were looking at these 2 bits here, well, we're now going to read in the first index in our indexes here, and that's going to be 04, and that's the final tile number. Now, if we were looking at these 2 bits here, well, that is index 1, and in this case, that would be using tile number 10 here. And so that's what this is doing. This is, at this point, has calculated the offset within the index that we need to read from. Here we've read in the index that we actually want to use. We're then adding IXL, which is the offset to the pattern data. That might be 0, or it might be something else. If we're using these backgrounds, we need to offset to avoid the font data, which might vary depending on the system. And then what we're doing is we are storing that in the destination tilemap HL, and we're incrementing HL. We're then repeating for the remaining bits that we loaded in that remain in C. And we're just going to shift 2 bits out each time to process the remaining horizontal tiles, because remember, there is a single, there are 4 tiles within each byte of our source data here. So this is a total of 4 horizontal tiles, and the next byte here is the 4 tiles below that, and the 4 bytes you see in this line here are the 4 lines within the super tile. So after we've done a single byte, if we've read in one of our bytes and processed it, we're then basically moving down to the next line by adding 32, and then we're repeating, and we're going to read in another byte and process that line. Now, once we've done an entire super tile, we're adding 4 to HL, our destination here, and that is effectively moving us across by 1 super tile, so that the next time this routine is run, we've moved to the next super tile across the screen. And once we've done the entire width, we'll have done 32 super tiles. That's why we're having to add that weird number when we move down by 1 super tile, because if you remember here, we were subtracting 32 because this routine would have been run 8 times and would have effectively skipped 32 tiles by itself. So that's how we are using the super tiles to compress the tile map here. Now, in some ways, maybe this wasn't entirely necessary for this game. It would depend on the system, and by compressing things as much as possible, it reduces the amount of bank switching I have to do. So it might always be beneficial anyway. But this kind of thing will become very important if you're doing a game like Super Mario, a game with scrolling levels, where you're not going to be able to store your tile map in an uncompressed format. You're going to need to find ways of making it smaller, and Supertiles is one of these. Super Mario actually uses 2x2 super tiles. That's partially related to the colors as well on the NES. The NES is limited to the number of colors. You have to have a 2x2 grid of tiles with the same color in most cases. So that's the super tile format that the Super Mario uses. It uses other tricks as well with regards to how it compresses its tile map data, but the point I'm making is this is going to, if you just having a game that doesn't scroll, you maybe don't need to do this kind of complex stuff. But if you are having scrolling levels, you will need to start thinking about this. Now, I know this has all been very, very complicated. I apologize for that, but I have had people in the past ask about how they can do things with regards to tile maps, with regards to scrolling and things, and unfortunately it becomes extremely complicated, and so there are really only 2 answers I can give. I either don't do it, find a simpler game to write, or you're going to have to start thinking about this kind of thing. And you know, what I've shown you today is one solution that I've come up with. I'm not saying it's the best. I'm not saying it's the one you should use, but I think it's at least worth you started looking at and starting to think about. And I'm sure you can come up with your own solutions that are appropriate for your needs and skill levels. If you need something simple, I'm sure you can work something out. And if you're far smarter than me, and I'm sure there's plenty of people out there who are, I'm sure you can come up with something far better. But anyway, as always, you can go to my website and download the examples and the scripts for today, and you can have a go with it. And we'll be looking at the tilemap code, the software tilemap code, in a later tutorial, the min-tile tilemap, which on a system like the Amstrad CPC is a software tilemap, but on the Sega Master System it uses hardware, and it also does the sprite graphics as well, including horizontal flipping. So it might be something interesting. Anyway, thanks for watching today. Have fun now, and goodbye.